Solution concentration. Well, we've got qualitative and quantitative descriptions. The qualitative descriptions would be dilute and concentrated. So a dilute solution is going to have relatively small quantities of solute. The concentrated is going to have relatively large quantities of solute. These are just relative terms. And then there are many different measures to quantitatively indicate the solution concentration. There are some of them. So we've got molarity, molality, mole fraction, mole percent, and parts by mass and parts by volume. So we've used molarity, right? We needed that for solution stoichiometry, but some of these others are a little bit new. So let's look at these. So this is a review of molarity. Molarity is the amount of solute in moles, the unit has to be moles, divided by the volume of the solution in liters. Molarity is slightly temperature dependent because the volume of the solvent will change. So liquids, as they are heated up, will generally expand slightly, and so molarity will increase slightly with temperature. Most of the time this isn't a problem, but there are some applications where that would be a big deal. Here's illustrations of how you would make a 1 molar solution of sodium chloride. And this was also covered in section 4.4. Molality is a concentration unit used that's independent of temperature. So where temperature dependence is important, we use molality, and that's very similar, that word is very similar to molarity. So if you see molality on an exam, do not assume that that's a typo and that I meant molarity. Pretty careful about those. This is the amount of solute in moles, so that's the same. But here we're going to use the mass of the solvent in kilograms. Not the mass of the solution, the mass of the solvent in kilograms. This is abbreviated with an italicized lowercase m, as opposed to a non-italicized uppercase m. That's not confusing at all. You kind of have to use context so that you know, is that supposed to be meters or molality? Parts by mass. So that is looking at the mass of the solute divided by the mass of the whole solution. And then we're going to multiply it by some factor. So if we have percent by mass, percent is per 100. So this is the mass of the solute over the mass of the solution times 100. This follows that same pattern of the part divided by the whole. So you have the part that you're interested in divided by the whole thing. Parts by mass, you're looking at the mass of each. The mass of the solute divided by the mass of the solution, and then you multiply it by a factor, and which factor you use depends on how concentrated the solution is. So percent by mass, we're multiplying by 100. So if you have something that's 14% by mass, then it has 14 grams of solute per 100 grams of solution. You could use kilograms, 14 kilograms per 100 kilograms. You could use troy ounces. You can use any unit of mass. They just need to be the same. You could use milligrams, nanograms. Parts per million, instead of multiplying by 100 like parts per 100%, we multiply by a million. This is abbreviated ppm, parts per million. Parts per billion, you multiply by 1 billion. So if something is 15 parts per billion by mass, that means 15 grams of solute per billion grams of solution. This is the sort of unit that's used for measuring contaminants in drinking water. You know, there's a level of lead that's acceptable in water, and it's down in the parts per billion range. Not very much. Parts by volume. Here you're looking at the volume of solute and the volume of the solution, again multiplied by a factor. You could have percent by volume, parts per million by volume, etc. So 22% ethanol by volume means 22 milliliters of ethanol in 100 milliliters of solution. There's another one as well, mass volume. So you can do parts by mass volume. So this would be mass of solute divided by volume of solution times a factor. These different parts units are used because they're easy for making solutions. So if you're trying to do 22% ethanol solution, you measure out 22 milliliters in a graduated cylinder, you add water to 100 milliliters, you mix it up, you've got your solution. These solutions generally don't need to be super precise. Percentages are used a lot in medicine. For example, a normal saline is 0.9% by mass sodium chloride. So to make a solution like that, you don't have to do a lot of calculating. You weigh out 0.9 grams of sodium chloride, and then you add water until the whole solution weighs 100 grams. And you've got your 0.9%. So these units are used because they're easy to make the solutions. They're not as useful in chemistry. If we're doing solution stoichiometry or something, we're going to have to do a lot more calculating here because we need the moles. That's why molarity and molality are used so much in chemistry. I think we've got an example here. So what mass of sucrose in grams is contained in 355 milliliters, 12 ounces of a soft drink that is 11.5% sucrose by mass? Assume a density of 1.04 grams per milliliter. These sorts of questions end up being just messing around with units problems. So we need to identify what we've got and what we're trying to find. So let's write down what we're given here. So we're given 355 milliliters of soda. Soda is shorter than soft drink. The 12 ounces is just kind of for interest. That's a 12-ounce can. We don't need the 12 ounces. 11.5% sucrose. And it says by mass. So that means 11.5 grams of sucrose per 100 grams of soft drink, soda. Because that's what percent means, per 100. 11.5% is 11.5 grams per 100 grams. And then we're given a density, 1.04 grams per milliliter. So what are we trying to find? The mass of sucrose in grams. So we're trying to find grams of sucrose. And we should make a path here. It may not be obvious what you should start with, but let's look at the units on these. Here I've got milliliters. Here I've got grams of sucrose per grams of soda. That's got a per in it. Grams per milliliters. Numbers where the units have per, those are probably supposed to be used as conversion factors. I can't use this as a conversion factor. So that's a big clue that that's what I want to start with. I'll get rid of this. So I'm going to start with milliliters of soda. Then I have to figure out how to get to grams of sucrose. Well, this density, grams of what per milliliter of what? What does that density refer to? Assume a density of 1.04 grams per milliliter. Is that the density of sucrose or the density of the soft drink or what? It's not the amount of sucrose per milliliter of soda, because that would, the mass of, that wouldn't work, because that would be like equal amounts. This is the density of the soda. So that's grams of soda per milliliter of soda. So this would allow me to convert milliliters of soda into a mass of soda, right? So I could go from milliliters of soda to grams of soda. Can I go from grams of soda to grams of sucrose? Do I have one that gives me that? Yeah, this one right here. The percent by mass gives me the relationship between mass of solute and mass of solution. I almost said the wrong word. Solution. So we can do that. Any questions about that process of figuring out where we're going? That's the hard part. Write these out. Write the units out. Write what the percent means so that you can see what you've got here, and then it's a matter of putting things together to come up with what you want. So we're going to start with milliliters of soda, 355 milliliters of soda. And we're going to convert that to grams of soda. Milliliters of soda will be down here. So the units cancel out. From grams of soda, we're going to grams of sucrose. And we'll have grams of soda down here. Get the units in place first, and then put the numbers in. So this is the relationship between grams and milliliters. Is 1.04 grams of solution per 1 milliliter of, grams of soda to 1 milliliter of soda. And then over here we've got 11.5 grams of sucrose per 100 grams of soda. This is not the only way you can set this problem up. Some of you are real good with percentages and stuff, and you can just string these together. You should still write it down, though. Okay, you should still write it down. So we've got 355 times 1.04 times 11.5 divided by 100, 42.458. Sig figs would be 3, so 42.5 grams of sucrose. The 355 milliliters, because it has a density of 1.04, is going to be roughly 355 grams. And this is smaller than that. If you end up with a mass of your solute that's larger than the mass of the solution, that's impossible, and you probably got something backwards. Any questions?